Hello, welcome to Pavinars. My name is Andrew Bram, and today we're going to talk about life cycle cost analysis, and it is a 2021 update. The original LCCA, or Life Cycle Cost Analysis Pavinar, was held and recorded September 4th, 2012. It was posted on YouTube September 10th, 2018, and it now has over 1,000 views, so thank you. With that amount of views, however, I am updating the previously recorded Pavinars, so we now have a new 2021 update. Today we'll start with a little bit of background, and that includes why is an LCCA important, and we'll go over the LCCA process. We'll then go into the theory of LCCA, and this includes both the inputs and the outputs. So what information do we get, and what information do we need in order to perform a life cycle cost analysis? We'll provide some examples, which is cheaper, going over multiple examples of multiple different types of pavements. And finally, we'll take a look at some more resources. There are a lot of very good resources out there on life cycle cost analysis and pavements, including from FHWA, Caltrans, roadresource.org, and various reports and papers. And remember, LCCA stands for Life Cycle Cost Analysis. So let's jump into why is a life cycle cost analysis important? Well, an LCCA provides an overall long-term economic analysis. It includes both initial costs and discounted future costs. And what an LCCA does is it attempts to identify the best value over some sort of time period. One nice thing about an LCCA is it only considers differential costs among alternatives, so any sort of common costs do cancel out, and this can simplify things pretty nicely. Other potential quantifications that you may hear along with LCCAs are benefit cost analysis or benefit cost ratio, an internal rate of return, a net present value, or equivalent uniform annual costs. And actually, some of these terms are used in an LCCA as well. But why are these terms, why are these quantifications important? Well, potential quantifications include the benefit cost analysis or benefit cost ratio, and this is where any number greater than a 1 indicates that the benefits exceed the costs. The internal rate of return, this is a rate that is necessary in order to make the costs and benefits equal. So when you look at varying rate of returns, discount rates or interest rates, what rate is necessary in order to make the two numbers equal? The LCCA also includes concepts around the net present value or net present worth, and this is the value of the expected net benefits, which are the benefits minus the costs. And at the end of the day, you want a positive net present value. And then finally, equivalent uniform annual costs. This is the net present value as if all costs and benefits occurred uniformly throughout an analysis period. And this is very useful if budgets are annual. For example, a lot of state agencies need to set annual budgets, so you can take these net present values and extrapolate them over multiple years into uniform annual costs. Something that's very important to talk about is the length of your analysis, or what's called the analysis period. And generally what you see is a graph like this, where on one axis you have the pavement life in years, and then on the y-axis you have the pavement condition. There is some pavement condition which indicates a terminal serviceability, or the road is no longer usable for traffic, so that's some sort of minimum pavement condition. And you can put general pavement conditions on the y-axis. So example, a PCI or pavement condition A is the best. A PCI of C is getting lower. And a lot of places say a PCI of D is the terminal serviceability. And you can see here, this is two different pavement design alternatives. If you have a roadway, you can put a chip seal on it, or you can perform a 2-inch overlay. Over time, The pavement will deteriorate until you apply the treatment, and then the pavement, in theory, should go back up to an A rating. And you can see here, the 2-inch overlay you apply when your road reaches terminal serviceability, but a chip seal you actually apply a little sooner when the road is in slightly better condition. Chip seals tend to be applied more frequently, however, they're less expensive. So you apply a chip seal at 6 years, 12 years, 18 years, and so on, and you can compare that to a 2-inch overlay, which is applied less frequently, but it tends to be more expensive. And you can see here a 2-inch overlay is applied at year 11, year 22, and these go on and on for as long as your analysis period is. And this is a very common plot. However, there are a lot of details and assumptions that go behind this plot, and this is what we'll be talking a lot about in this presentation. So some common terms that you'll hear when we're talking specifically about a life cycle cost analysis is the initial cost, the user costs, what I call annual maintenance and scheduled maintenance, scheduled rehabilitation, we just talked about the analysis period, and then finally the salvage value. And this can also be represented graphically. So graphically, the common LCCA terms is you have time, again, on your y-axis, and then you have costs. Time is on the x-axis, and costs are on the y-axis. And you can see you have some sort of initial cost, and that includes both the user and the agency cost. And here the agency cost is shown as a solid arrow, and the user cost is shown as the dashed arrow. So there's some sort of initial cost at year 0. Then every year you have some sort of annual maintenance cost. And this can be anything from clearing tires off the side of the road to checking drainage in your road. All of these things are done on an annual basis, maybe biannual, but they're done regularly regardless of the road condition. At some point, you'll have some sort of what I call scheduled maintenance, which is maintenance number 1. So there's some sort of cost associated with that, along with the user cost. And then at some point, you may need to do a rehabilitation or a scheduled rehabilitation. So there's some sort of cost associated with that from the agency perspective, plus some sort of user cost. And then at the end of the analysis period or the end of the pavement life, you remove that pavement, and there's some sort of salvage value because there's some value in that material that's on the roadway, and if you take it away, you can reuse the material. Recycled aggregate for concrete, recycled aggregate for asphalt, those type of things can be reused, and that has some sort of salvage value. And when you determine that salvage value, that determines your analysis period. So it looks like this is a 25-year analysis period. It includes 25 years of annual maintenance, it includes 1 scheduled maintenance, and it includes 1 rehabilitation, scheduled rehabilitation. And all of those have agency cost, which is represented by the initial cost, maintenance 1, rehab 1, and annual maintenance. And it has some sort of user cost, which is the dashed lines. So the annual maintenance, the scheduled maintenance, and the scheduled rehabilitation, these costs and times, so what time they occur in, what year, and then how high the areas are, those are all based on the treatment or the activity that you're performing on the road. And the goal of a life cycle cost analysis is to take all these annual maintenance costs, all these scheduled maintenance costs, all the scheduled rehabilitation costs, and the salvage value, and bring all those costs back to year 0, the present, and you can directly compare different alternatives, different sequences of treatments and activities. So that's a little bit of a background of life cycle cost analysis. Now let's dig into the theory of life cycle cost analysis. The life cycle cost analysis can be broken down into 8 steps. The first step is to develop maintenance and rehabilitation strategies or treatments for the analysis period. The second step is to establish the timing or the expected life of those various strategies or treatments. The third step is to estimate the agency cost for construction, maintenance, and rehabilitation. You then estimate the user costs. You develop an expenditure stream. You compute the net present value. You analyze the results, and you can use either a deterministic or probabilistic approach. And then you evaluate strategies and develop new ones if necessary. So let's briefly walk through these 8 steps, and this will provide the foundation of the theory of life cycle cost analysis. So maintenance and rehabilitation strategies. We're going to take a look at both flexible maintenance and rehabilitation strategies or treatments and rigid maintenance and rehabilitation strategies. And for flexible pavements, we're using the resource roadresource.org. That's a website. If you go to roadresource.org, you can see all sorts of great information. And for rigid pavements, we're using the NCPTC Concrete Pavement Research Guide. For flexible pavements, you have various maintenance treatments. You have fog seals, rejuvenating fog seals, slurry seals, microsurfacing, chip seals, scrub seals, cape seals, thin lift, standard, and bonded HMA overlays. And then for rehabilitation treatments, you have hot in place recycling, cold in place recycling, full depth reclamation, and remove and replace. On the rigid side, from the Concrete Pavement Preservation Guide, they divide categories a little differently. Instead of maintenance, they have preservation, and that's joint resealing and retrofitting edge drains. Functional is kind of a combination of maintenance and rehabilitation. With functional, you can do partial or full depth repairs, you can do diamond grinding or diamond grooving, and you can do a thin concrete overlay. And then structural is squarely in rehabilitation. You can remove and replace, you can do soil stabilization or jacking, and you can perform a dowel bar retrofit. Now, deciding what sort of maintenance or rehabilitation treatments, or preservation, functional, or structural treatments you'll apply, you need to consider your analysis period. An analysis period can be as long as you want. It can be as short as 5 years, and it can be as long as 50 years or even more. So it's really up to the person performing the analysis how many years in the future do they want to look out. But that analysis period is very important to keep in mind when you start digging into the treatments and the established timing or the expected life. And this is where things get a little bit tricky. And let's start with flexible. We have some treatments here. We have fog seals, slurry seals, chip seals, hot in place recycling, and full depth reclamation. And if you go to roadresource.org, you can see it actually has a variable lifespan. A fog seal can last between 2 to 4 years, a slurry seal 5 to 10 years, a chip seal 1 to 10 years, hot in place recycling 4 to 15 years, and full depth reclamation 5 to 25 plus years. So that's a pretty wide range of lifespans. And you can do the same thing for rigid pavements. So let's take a look at joint sealing, diamond grinding, and a thin concrete overlay, which is 4 inches. The lifespan of joint sealing can be anywhere from 3 to 10 years. Diamond grinding can be 16 to 17 years, and thin concrete overlays are anywhere from 15 to 20 years. Now, flexible treatments have roadresource.org. This is an incredible website that has a lot of information in one place. Rigid pavements aren't quite as straightforward. The lifespan and costs are kind of hard to find for rigid pavement treatments. And so this is from Caltrans, the Asphalt Concrete Pavement Association, and FHWA. Now, I hope a question you're asking yourself is, why is there a span of life? Shouldn't we know how long a fog seal lasts? Shouldn't we know how long a diamond grind lasts? Well, the span is there because it is dependent on existing pavement conditions. So what's the existing pavement condition that you're placing the treatment on? The traffic, the climate, materials used, the construction practices, and so on. So there are a lot of different variables that go into determining what the potential lifespan is of any one given treatment. Now, if we do start to establish potential lifespans, we then need to talk about the agency costs. And this is also tricky. From roadresource.org, we're going to look at the same 4 treatments. And in 2020, roadresource.org gave national averages for each one of these treatments. So you can see a fog seal's 57 cents a square yard, all the way down to FDR with 4 inches of HMA is 28.54 a square yard. Again, rigid treatments are a little harder to find. These are actually from arkansashighways.com, and it was cost from 2019. Joint sealing is $3.05 a foot, all the way up to thin concrete overlays, which is anywhere from $23 to $58 a square yard. So just like lifespans, the costs of rigid treatments are hard to find, and this is just one agency's, RDOT's, costs. Now, when you're looking at these costs, something you definitely want to keep in mind, does these numbers include just materials, or is it materials and construction? So whenever you find a number, you need to recognize, well, what is actually in that number? What information, what assumptions did they make while developing that number? Because once you start modifying either the expected life or the cost, you can influence life cycle cost analysis significantly. And we're going to see a lot of examples of that later on. So nailing your lifespan and your costs is very important. Now, this is just agency costs. We can also take a look at user costs, and there's a couple different categories when we talk about user costs. One is delay. Whenever you perform any sort of construction, there's some sort of restricted capacity, there are idling costs, and these all have a value of time. And so again, turning to RDOT, Arkansas Department of Transportation, they estimate a passenger car to be worth approximately $18 an hour, and they anticipate a truck to be worth about, they say 24 to 25, they say $24 to $25 an hour, so around $24 an hour. The point here, though, is that there is some sort of value associated with passengers and trucks, which have both a passenger and some sort of cargo with them. In addition to delay, there are vehicle operating costs, and all of the costs I found for vehicle operating is somewhere in the cents per mile range. So it's anywhere from 25 to 75 cents a mile, so this depends on the work zone length. And vehicle operating costs change with pavement conditions, and in general, rougher roads increase vehicle damage, therefore rougher roads increase vehicle operating costs. And then the biggest ticket items are accident or crash costs. And the numbers I found, property damage is around $3,500. Non-fatal injuries can be around $40,000. And if there's a fatality, it's around $2 million. So you can see this is where the costs really start getting high very quickly. And they range greatly, but this gives you a general trend of where the 3 different crash costs are. Now, when we think about user costs, however, in general, delays account for greater than 95% of user costs. So that first category up there, that accounts for the vast majority of the cost. And the other two, while they do occur, and when they do occur, especially with the crash costs, they need to be addressed, but they're a relatively small percentage of the overall costs. The next step is to develop an expenditure stream. And this is one expenditure stream for flexible pavements. And you can see here every 6 years a chip seal is being applied. And at year 20, cold in place recycling is being applied. And then at year 25, there's some sort of salvage value. And these all have both initial or agency costs. The agency costs are the initial costs, the chip seals, and the CIR. And then you have user costs at each time as well. And you can compare this to another scenario. This is also a flexible pavement, but here at year 8, they place an ultra-thin HMA overlay, and at year 18, they place full depth reclamation. And again, there's some sort of salvage value at 25 years. So you can see both flexible pavements, but instead of placing 2 chip seals in CIR, you place one ultra-thin HMA and one FDR. So this is just an example of how we have two different potential scenarios, and there are different costs and times associated with these scenarios. And I'm not claiming that these are good treatment selections. This is for demonstration purposes only, just to show that you can have one road, but you can solve any sort of potential issues with two different strategies. Once you have these two different scenarios or more, you can compute the net present value, or the NPV. And the net present value starts with your initial costs, and those initial costs are both the agency and the user costs. You then have a maintenance cost, which is annual, which is every year, and this includes the discount value, which is in decimal, the year, and design life, which is the years of your analysis period. So you can see this is the annual maintenance, and it's done every year in year 1, in year 2, in year 3. But in addition to the annual maintenance costs, we have scheduled maintenance, and this is in any year N, depending on the treatment that you're going to place. And again, you also use the discount value, which is in decimal, and the year that it's applied. You have scheduled rehabilitation costs, also in year N. And you can see that we're adding all of these together. We have the initial costs, the maintenance costs, and the rehabilitation costs. But then we subtract the salvage value, which is at the end of life, or the end of the analysis period, T. And the salvage value can be computed with this equation. In this equation, the CLT is the cost of the last treatment, the RLLT is the remaining life of the last treatment, the SLLT is the service life of the last treatment, and the CRI is the cost of the lower layers remaining from initial construction. So you can see here essentially the last treatment that's applied decreases linearly every year in cost, and that value is then added to the cost of the lower layers remaining from initial construction. Once you have your net present value, or NPV, you can analyze your results, and this includes either a deterministic approach, which does not account for any variability of inputs, or it can be what's called a probabilistic approach. And the probabilistic approach incorporates variability of both agency cost and user costs, treatment life, interest rate, and any other input that can be put into the analysis. And this is very interesting because if you're talking about an initial cost, you can understand where an initial cost does vary based on a whole host of different scenarios. And so there's some sort of distribution associated with the initial cost. And this could be variation in potential weather during construction, uh, significant delays for the time of traffic during the construction, any sort of things like that can happen, and that'll give some sort of variability. So there's variability not only in the initial costs, but also in all of the future costs as well. Future raw material costs, future construction costs, future traffic levels, future inflation rates, interest rates, discount rates, all those type of things have some sort of variability. So you have all this variability within each category, and when you put them all together, when you sum them together, there's some sort of variability associated with the net present value, or the NPV, and that's a probabilistic analysis. Regardless, however, if you do a deterministic or a probabilistic analysis, you want to compare net present values, you want to choose, or you want to reevaluate the different strategies that you laid out. So that was quite a bit of theory, but it's important now to go over that theory because now we can go over some examples. And a very common question is, which is more expensive or which is cheaper? Here is a flexible pavement. This is Arkansas Avenue. It's in Fayetteville, Arkansas. It's on the east side of campus, and it is a flexible or an asphalt pavement. Here is a rigid or concrete pavement, and this is actually Maple Street, also in Fayetteville, Arkansas, and this is on the north side of campus. So this is a very common question I get. Which is cheaper, flexible or rigid pavement? Let's look into it. What do people say? Now, before we look at actually any numbers, we do need to ask the question, what goes into these analysis? Because it actually isn't as straightforward as a which is cheaper, A or B. It's not that easy. There are a lot of dynamic or variable inputs. For example, what are future raw material and future construction costs going to be? What are future traffic levels going to be? How will the in-service pavement actually perform over time? Will there be any significant weather events during that time? Will the time value of vehicles change over time? So they may be worth something today, but will they change 20 years from now? What sort of innovative products and processes will be developed that may reduce costs in the future? Although we lay out certain maintenance and rehabilitation treatment schedules, what if those change? That will change the net present value. Also, will the inflation, interest, or discount rates change in the future? You bet they will. So how do we account for that uncertainty? And this list could go on. In addition, all of this is assuming a perfect design, perfect production of materials, and perfect construction. And I don't know about you, but I've never been on any construction site that had a perfect design, perfect production, and perfect construction. Whether it's horizontal or vertical construction, there are always things that are going on. However, let's go through some examples of rigid versus flexible pavement. Here's a nice one from 2000. This is from the state of Texas. And you can see that they explored 3 different discount rates, 4%, 7%, and 10%. And you can see here they looked at both hot mix asphalt and Portland cement concrete. And they found that HMA costs less than PCC. Now, I will give you all the full citations later of these studies. This is the 2000 Texas study. Let's jump 10 years into the future, though, and we'll see a very different story. Now, this was done by Jim Mack, who worked with Cemex, and he looked at an Arizona DOT rehab job. So let's start over here at the far left. You can see they looked at the total net present value using an interest rate of 4%, and here asphalt cost a little bit more than concrete. Looking at an inflation rate and an interest rate of 4 and 8% respectively, again, asphalt costs a little more than concrete. Looking at different inflation rates, but the same inflation rate, again, asphalt costs more than concrete. And then looking at a MEPDG, Mechanistic Empirical Pavement Design Guide rehab strategy over 45 years, you can see here the PCC was 37.2% lower. So going from the left to right, we're at 6.8% lower, 7.6% lower, 24.5% lower, now 37.2% lower. Now, I do hate to mention this, but Cemex is a concrete company, so these results shouldn't be a surprise, but it does show how changing the interest rate and the inflation rate can really modify your analysis. Changing the design strategy, Arizona DOT versus MEPDG, changes the analysis. But this study, PCC, costs less than HMA. Let's take a look at a 2011 California study. Here we have a couple different treatments, and we're getting a little more in-depth into the nitty-gritty details. Here we have an asphalt concrete pavement, ACP, and we had an innovative or long life strategy. FDAC is full depth asphalt concrete, and SCOL is crack, seat, and overlay. So here you can see the innovative asphalt concrete pavement costs approximately $40 million. A standard asphalt concrete pavement with all those same categories, the agency costs for both FDAC and CSOL, the annual costs and the user costs, costs about $49 million. And then the long life PCCP, Portland Cement Concrete Pavement, costs about $60 million. So here, HMA costs less than PCC. Now, jumping 9 years into the future, another California study, and look at this, HMA costs more than PCC. And here they did 2 different analyses, and this is actually a very nice paper. They looked at a linear material cost increase versus a statistical model that they developed based on previous material costs to try and model future material costs. So you can see here the predicted, regardless, is the same trend as the uniform. The HMA is more than the PCC. Another way to say that, the PCC is less than the HMA. Now, finally, we're going to finish with a bunch of examples from Minnesota DOT. This is all done in 2020. They have a very nice document that have many different projects that they analyzed. And these are all where HMA is the existing pavement. These 6-digit codes along the y-axis are state project numbers, but here you can see they looked at an HMA overlay, a PCC overlay, and hot mix asphalt on either FDR, full depth reclamation, or CIR, cold in place recycling. And you can see the HMA overlay is always less than the FDR or CIR, and those are always less than the PCC. Now, what if you have a PCC existing pavement? Don't fear, MnDOT took a look at some jobs as well. They looked at 2 jobs here. They looked at an HMA overlay, which should last 13 to 15 years, a PCC overlay, and HMA overlay that will last 20 years. So they're looking at 2 different treatments, and they're looking at different analysis periods and different lifespans of the treatments. And you can see here the HMA overlay is less than the PCC overlay. But if you look at job 8680-173, also a PCC existing pavement, they looked at new hot mix asphalt versus new PCC plus a PCC overlay at 2 different analysis periods. And you can see here that HMA is almost $20 million more expensive than PCC. So in the same report, MnDOT showed that PCC was less than HMA. So this is amazing. We've been bouncing back and forth during different time periods, different agencies, and we've seen differences, and you can make some sense of that because they're different climates and all of that. But here, one agency in one report shows that sometimes HMA is less, sometimes PCC is less. Now, all of these primarily focused on simply Portland cement concrete versus asphalt concrete, flexible pavement versus rigid pavement, HMA versus PCC. Let's take a look at some different treatments. So this analysis was done on the entire Arkansas highway network in 2021, and this was an academic study, so it wasn't actually executed, but it does show the power of different treatments. So for conventional treatments, we placed chip seals on all the PCI A and B roads. We placed minor mill and fill on all the PCI C and D roads. And we placed full depth remove and replace, or R&R, on all the PCI F roads. This is the conventional treatment package. For optimized, depending on the highway type, we put rejuvenating fog seal on all the PCI As. We put microsurfacing on the freeways, scrub seals on the multi-lane highways, and chip seals on the 2-lane highways, all on PCI B. And then we also did various treatments on C, D, and F, including minor mill and fill, cold in place recycling plus chip seal or place hot mix asphalt, full depth remove and replace, and full depth reclamation plus hot mix asphalt. So conventional only used 3 treatments, which are very commonly used in Arkansas. The optimized used a whole suite of treatments. And you can see here that the conventional treatments over a 50-year analysis on all freeways, multi-lane highways, and 2-lane highways cost about $90 million over 50 years to apply these treatments to the entire network on a regular schedule, whereas the optimized treatment plan costs about $82 million. So even changing the treatments over a time period can get you some different results. So what do you think? What is cheaper, flexible or rigid? It depends. Remember, there are many dynamic variables: future raw material and construction costs, future traffic levels, pavement performance, weather, the time value of vehicles, innovative products coming down the tubes, maintenance and rehabilitation schedules, interest rates, discount rates. It goes on and on. So, of course, as any good researcher says, more research is needed. I just went over maybe a half dozen examples of, depending on what assumptions you make, depending on when you perform the analysis, you can show different trends based on different assumptions. Now we're going to move from some of the examples of the life cycle cost analysis to resources. So if you search FHWA life cycle cost analysis, the Federal Highway Administration has a great website for life cycle cost analysis. They have a primer, a fact sheet, they provide 3 case studies. There's a very seminal interim technical bulletin, life cycle cost analysis and pavement design. This is what I used to write a lot of this presentation, and it was released in 1998, but it shows that we've understood these concepts for a while. And if you want to look at that directly, you can just Google the FHWA SA 98079. That sequence there, that's the report number, and that report will pop up. But it's also posted on their website. And FHWA also has a lifecycle cost analysis software. It's called Real Cost, and that includes a user manual. You'll be happy to know that that incorporates probabilistic modeling, so you get a little bit of that uncertainty analysis. Caltrans is another great resource. You can search Caltrans Lifecycle Cost Analysis, and you can find their procedure manuals from 2013. And the reason I like this procedural manual, I really hope they update it, even if that makes this webinar look dated almost immediately, but I really hope they update it because they have dozens of tables in this document with different pavement types, different climate regions, different design lives, different annual maintenance, scheduled rehabilitations, costs, and timing. So a lot of those assumptions that I said that are hard to find, when to apply treatments and how much do they cost, California has dozens of tables already established. Now we could have a very robust discussion as whether or not those tables are correct or incorrect, but they're a starting point. They have some engineering robustness behind them, and they're a great way to kind of look at some different trends. So I definitely encourage you to check out the procedures manual that can be found through Caltrans. And then finally, I highly encourage you to look at roadresource.org if you have not already. This is, I think, a textbook for flexible pavement treatments. It has all the flexible pavement treatments on there. It has a discussion about their design, their construction, their in-service. It has pictures and videos. It has case studies. It has 4 calculators, including equivalent annual costs, a life cycle analysis, remaining service life, and cost benefit value. It is a phenomenal resource. So go check it out, roadresource.org. Now, I did promise I'd show the references from all the examples. Begg et al. Wrote the Texas study in 2000. Mack, his presentation was in 2010. Lee et al. Was a transportation research record paper released in 2011. Kim et al. Was the Caltrans report from 2020. MnDOT released their report in January 2020 as well. And then my grad student and I, Sadie, Dr. Casillas, she and I have had a paper. It's in its 2nd review. Hopefully it will be accepted to the Journal of Transportation Engineering Part B Pavements. But if you want to, take a screenshot of this and you can dig into all these resources. They're all phenomenal resources, lots of interesting information in them, and I highly recommend that you check them out. So we've covered a lot of ground today. We've talked about the background of LCCA, the theory of LCCA. We've shown a bunch of examples, and you have some more resources. So I appreciate you joining us, and I hope you have a great day.